Actually, before we plot this, I just want to go over here. In this calculation folder, we're going to see that the margin of error when we look at it, or for the actually we're going to look here down here at the required sample size, that we're going to do some z-score over the margin of error, but we're going to multiply p times 1 minus p. And that's what we're doing here. And so it's maxed out at 50%. And then the other thing I say over here is, so the closer the true population is to a 50-50 split on an idea, a support for, do you support cloning of humans? Do you support stem cell testing? Do you support whatever, people wearing masks? Like whatever you feel, like whatever the survey's asking, the closer it is to the 50-50 split, the larger the sample size you will need to estimate the true population proportion. And if the population is split 90-10, you can get by with a smaller sample. And so what I just say is, in fact, you will need a sample size 2.8 times larger to get the same margin of error for a 50-50 versus 90-10. And that's just taking this 0.25 and dividing it by that 0.09. And just remember that, because later on we're going to calculate a required sample size, and I'm just going to show you that that is in fact true. But we'll just go ahead and I'm going to put this on the x-axis. Let's see, and I'm going to put p times 1 minus p on the y-axis. So we're just going to go ahead and insert a scatter plot, and we'll just go ahead and fill out the lines. Okay, and then so that is going to be. Now we're going to go ahead and right click on it. We're going to click select data, and now what we're going to do is edit, and the x values are going to be this. And let's just make sure that does what we want. Okay, so it looks like I've made a mistake here somewhere. Let's go ahead and select and look at why is that. Okay, so the proportion and the y value. Oh, okay, so this is off by 1, and that's why. Okay, so if I change that to an 8, so it's not including the header for the x values, then, okay, boom. Okay, so we could change I'll just go ahead and we'll change the format the axis here. I'll go ahead and hide myself. Okay, and so now it's saying the max here is 120, which is why it's saying that. Okay, and now if I hit enter, that should take it down to 100%. And then let's just go ahead and add up here. This is going to be the required, go ahead and hit that, but required sample size as function population proportion. Okay, and actually, so this is this p times 1 minus p on the y-axis, and this is the population proportion here on the x-axis. I'm not going to take the time to label this, but let's just go ahead and we'll go ahead and put a shape outline just to see it easier. But all this is saying is it's maxing out here as we get to 50%, and then as we get closer to either one of the tails, we can get by with a smaller sample size. Okay, and we're going to end up coming back to that. So then I want to show you. Down here. We're going to end up creating. I'm going to end up kind of recreating this, but I want to have you. We're going to do it with me. So we want to look at this normal distribution approximation, and the fundamental principle by that is that I want to have at least 5 successes and 5 failures in my sample. But I want to walk through the mechanics of this first, and then I have this example over here in the yellow box that I'll talk about. So we'll just go ahead and do. I'm going to set this box equal to my sample size here, and I'm just going to say it's equal to that, and we'll do F4. Okay, and then we'll just take it down, and then we'll make this to be equal to, let's do 1%, we'll do 2%, 5%, and then we'll start doing 10, 15, and we'll go down in 5% increments down here till we get close down to, oh, I don't know, say we'll do till we get down to 95%. So we'll go down, da 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 da. Okay, now we'll do 95%, and let's do 98%. Actually, let's do 97.5%, 99%, and 100%, and then I'm going to change this guy to be 2.5%, and you'll see why in a second. This guy just gets copied. We just touch on that bottom right corner, bring it all the way down, and then this is obviously just going to equal is just going to equal 1 minus this guy. Oh, sorry, we're doing NP. We're not doing one. We're doing NP. So this is we're going to actually multiply 228 times this. Okay, we'll bring that down, and then and remember the threshold is 5. That they want NP to be greater than 5, greater than equal to 5, and N times 1 minus P equal to. And so we're going to do equals to this. I'll bring that down. Oops. Okay. Now I can bring that. I'll bring that down in just 1 second. So now we're just going to do this is equal to 1 minus this guy. This is equal to this times this. So let's see, is this guy an absolute? All right. I'm just putting a space in between here to help me keep them apart. Okay, and then what we should see is now I'm going to use that AND function that we talked about last time to equal. I'm going to use that function we used last time to test whether they're both greater than or equal to 5. So we're going to say AND. Okay, we're going to say is this guy greater than equal to 5, and is this guy greater than equal to 5. Okay, so we're getting our true values here or not, and I'm going to change this now back to 10 so that we get a whole bunch of false and trues. And now what I'm going to do is I'm going to select, I want to make it so that I could use, conditional formatting to say highlight rules, whether the text contains or value is equal to, and I think actually we would have to say true. Okay, because it's not actually containing the text true in there, it's that the value is set to true, much like something is set to 5. So now we'll just go ahead and conditional formatting, and I'm just going to go, I'm going to just clear that rule here. We'll just go ahead and make sure that when we manage the rules, I'm going to just go ahead and delete that rule. Okay. So now what I want to do though is I want it to highlight the entire row if the value in column O is true. So I select the range that I want this applied to. We go up here to conditional formatting, and this time we're going to do what is called a new rule, and we're going to use a formula to determine which cells to format. Okay, and then here's the formula that we're going to do. We're going to say equal to, and I'm going to say O32, but I want it to just be not absolute value O and 32. I just want it to be to tell it the column O. And so I'm going to get rid of the $sign next to the 32, but leave the one next to the O. And I say equal to true. And true is not in quotes. It is just the word true. So O32 equal to true. We'll set some format. I'm going to pick, I don't care what color you pick. I'm going to end up picking this orange. Okay. So right now, when I have a sample size of just 10, I'm only meeting the normality if it's split 50-50. If I now say 20, okay, now it's all the way out to 25%. If I say 30, okay, and it's just going to highlight, and as I get bigger, this thing is just going to expand. I have to worry about meeting this normality function or this normality approximation less and less. Okay, and so you'll notice though that if I go out in 10, it kind of moves out symmetrically from the middle, right? So if I now do 20, you see, oh, it's 20, it goes up to 25% and 75%. If I do 30, it goes 80-20. If I do 40, it goes up 15-85%. And you're like, okay, well, why is that? Well, I actually started over here and I put some values of 10, 20. Right, and we'll just go all the way up to 100 here. Okay, and I went and said, okay, well, in the value in my table, this is what the P and the 1 minus P says. In the value in my table, if I put in 10, what is the minimum value in my table that I observe that it works for? And so for 20, it's at 25%, and at 30, it was at 20%. So I was like, okay, well, I'm just doing this by trial and error. There's got to be a a way to sort of come up with what is the true minimum, right? So I don't have to say, is it 17.5% or 7.5%? Like, what is the actual number? And then I was like, okay, well, there's got to be a math way. So I said, well, look, the formula is NP equals 5, and I noticed that it's going to hit it. The value that's going to kick it out is whatever this lower probability is, the low end of it, because that's what's going to get us below 5. So I said, well, look, if n is equal to 20, then np equal to 5 becomes 20p equal to 5. And so if I divide both sides by 20, I get the probability is going to be 5 divided by 20, which is 25%. And then if I say if I make that more general, for any np equal to 5, if I divide both sides by n, that probability, the minimum threshold there is going to be at 5 divided by n. So I'm going to say it's equal to 5 divided by my n value. So that's 50%, 25%. So we ought to look here at, let's look here at, say, 30. And I say, okay, well, let's go ahead and if I insert a column here, and I say, okay, well, I'm actually just going to take this whole guy, copy and paste it down, and I'll do it at oh, I don't know, let's do 17%. Okay, and so then it shows up at 30 because, so what I wanted here was what's the true value, not just the thresholds I was looking at. And so now you can see, oh, this is how this is going to, how this is, as we get smaller and smaller, this is the minimum threshold. And we could actually do 200 here. Just to see, okay, well, 2.5% is going to be the minimum that it can kind of pick up on. And I only mention that because the reason this normality function comes into play, and I'll go ahead and hide myself here, is that, and I took this first part of the question is actually straight off of a, this is from an AP practice test. And so they talk about, in the movie A Civil Action, which was probably before most of you were born, came out in 98. But it tells the story of this legal battle that took place in Woburn, Massachusetts, where a well had gotten poisoned by a corporation working there. I haven't actually watched the movie, but you can imagine the type of movie where big bad company either deliberately, pours their waste down the drain, or they don't take sufficient precautions and it accidentally goes down. And so then the question was, on the side of the town where that drank water from this well, there were 16 of the 414 babies that had birth defects, and on the west side, 3 of 228 had birth defects. And the success here, I put it in quotes because the success means, in this case, how many babies with birth defects do I see on each side? And on this side, I've got, on the east side, where they were drinking this water, 3.86% of babies had birth defects, and that 16 is greater than 5. On this side, they didn't. There were 3, thank goodness. So the normality approximation is not met here, at least for the west side. And this becomes more important in the next chapters when we start testing hypothesis, which is what we actually care about. Like, the whole reason we're doing all this is to be able to say, is this difference statistically meaningful? I mean, was it that chemical that was causing these birth defects, or was it something else, or how much did it contribute? And you'll also recall it doesn't. You need to have a random sample, and so what that means in this case is are the people on the west side of town equivalent to or good matches to the people on the east side of the town? So you can imagine, and in the movie, this is sort of the wrong side. The east side is the wrong side of the tracks, and so the people on the west side are going to tend to be wealthier and better educated, and probably more likely to get better medical care than the people on the east side. And so really what we would want to also see is, did they have about the same I write this here, did they have about the same percentage of birth defects prior to the water becoming contaminated, right? Because if they didn't, if the people on the east side had higher birth defects before, then some of this higher number now, the 16 versus the 3, could be due to other things. Maybe those on the east side also were more likely to have lead paint in their house, and so they were more likely to have birth defects. And so part of what we're attributing here to the water well is actually lead poisoning, right? There's lead paint in the walls, and so on. And so the z-score for this difference, you can go look it up. I'll put a link here where I actually went and calculated out the test a difference in proportions, right? And so, sorry, I did it right here. I'll put this website in yours, but the link is right here. But you can actually go in, and I put in, I'm looking over here, but I actually went in and put the, so you had 16 in of one group out of 414, 3 out of 228. I put it at a 0.05, and the z value is 1.8238, which means the p-value is 0.06, which is not significant if we're doing what we'll learn later is a two-sided test. It is significant if you do a one-sided. And so this is where all this stuff kind of becomes messy, is because nobody wants to see kids with birth defects. And so, like I say down here, we would want to find other ways to investigate. Like I said, if on the east side they had fewer birth defects than on the west side before, now you're going to say, that's stronger evidence that it actually is due to this well. Maybe can we look in other towns? Are there other towns that had poisoning from the same chemical? And do we see it there as well, right? So we would want to, given the importance of this issue and its birth defects and babies and human lives, we would want to investigate this further. But I just want to show you and give you an example of why this matters and why we're actually doing all this mechanical machinery stuff. Okay, so sorry for that little detour, but that's where we're at. So then this actual one is the most important one, where I want to show you how to calculate, and I do this all the time. Anytime I'm doing these repeated calculations over and over again, and I'm putting in p times 1 minus p and square root of n, I get tired of doing this calculation right here by hand over and over again. And so I create a little calculator. And in doing so, I think it also, again, helps us see what is going on under the hood. So this one, we are going to name a bunch of ranges. But again, on this one and on each of these, you'll notice, I didn't explain it earlier on. In this one, have used this input. Any place that I'm asking you or myself to put in a number, I'm having it I've put that with that input color. One of these days I'll go create my own because I don't particularly like this orange, but for now that doesn't matter. So we're going to call this true population proportion. We're going to just call this. Let's go ahead and call this P. And you say, can we do it with a single letter? Yeah, we actually can. And then this one I'm going to call N. So now I've got my sample size, I've got P and the proportion. The expected value, again, is if I were to take 100 samples of this, and the true population proportion would be 0.48, what would I expect to get in my samples? And the expected proportion I would find in my samples would be the same as the population proportion of 0.48, so I'm just going to say is equal to that. And then over here I'm going to put, and this is just to make it easier for me to see, so that I can see what P and 1 minus P are going to end up being. And I put these as percentages. It doesn't actually matter. Okay. So now I could say, let's do our little normality calculator, and let's say, okay, let's have Excel do the work for us. So we'll say, okay, well, this is going to equal N times P. Okay. This is going to say, this is going to equal N times 1 minus P. And then now we're going to do our AND function again, which is this greater than equal to 5, and is this guy greater than equal to 5? Okay. Now, we did this in class today for those who were there at the 10 a.m. session. I've changed this one a little bit, so people who are working on it may need to add a few. If you're using the one that I handed out in class today, there are a couple things you'll need to add, but I will show those to you. Okay. And then just like we did over here with our, making this orange, on this page I'm saying anything that is like this guy, anything that it is spitting out a value that I care about, that I'm having Excel calculate, I'm going to put in green. And then anything I'm inputting is going to be in this sort of creamsicle, orangey, whatever color that is. But we're going to now do this highlighting rule. We'll do the same thing with the conditional formatting. And in this case, we're going to put a new rule. And so we're going to say this guy, and we're going to say equal to, and in this case, because I only have a single row, I can just put $F, and what is that, 11? $11 equals true. And again, there's no quotes, and I'm going to pick this green and hit OK. And so if this guy, so let's go see why it's not doing what we want. So I've got F. Oh, it's F10. That is why. Okay, so let's go ahead and we're going to go manage those rules. Okay, so we're going to go edit the rule, and I just need to make that F10. Apply. Okay, boom. All right, so at a sample of 10, it won't meet the normality, but a sample of 20 or 30, anything bigger, it's now going to flag it for us. So what I love about this is now I can make Excel do the work for me. Now I need to do, now the standard error we're going to calculate, which is this guy right here. And so again, I can just do is equal to, I can do P times 1 minus P, okay? And then I'm just going to take the square root of that. Okay, now I'm going to take is equal to the square root of n. I can actually just put n in. Okay, and then the standard deviation is just this guy divided by that guy. The square root of this top stuff divided by the square root of the bottom stuff. So I'm going to equal, it's going to equal this divided by that. Okay, 0.0707. Okay, we'll just go ahead and make sure it's in the right one. And we're going to go ahead and call that, we'll call that the standard error. Okay. I do that for two reasons. One is it reminds me what the formula is, right? And it's easy to check if I've done it correctly or incorrectly. And then it makes it easier down here to refer to it. Okay, so now we're going to say if the true population proportion is 0.48, if I take 100 samples that are size 50, what percentage of those samples am I going to actually, is it going to return a population proportion of 0.55? Okay, instead. And so essentially what I need to do is say how big is the observed value from the expected value, so 0.55 minus 0.48, and then I divide it by the standard error to get a z-score. Okay, so we're going to do is equal to, and then we will call this the, let's go ahead and call this guy, we'll call this guy the sample proportion. Okay, so I've got NP sample proportion standard error. Okay, so now I'm going to say it's equal to the sample proportion minus P, the population. Okay, this guy is going to equal the standard error. I'm just going to bring it here, bring it down. Okay, and the z-score then is just going to be equal to this divided by this. Okay, which gives me, I'm 0.991 standard deviations above the mean. Okay, so we'll probably find about, I don't know, 30% in that range. This one I'm just going to do just to show you kind of something kind of fun. I'm going to use an if statement, and if says give me a logical test. Then if that's met, if this is true, what do you want me to return? And if it's false, what do you want me to return? In this case, I'm going to say, is this above 0 or less than 0? So I'm going to say, so if this is greater than or equal to 0, then I want you to return the value above. Okay, and if it's less than 0, I want it to say below. And you're like, don't I already kind of know that? The answer is, of course you do. I just want to show you some kind of cool things you can do with this, right? Which is, now I could actually use our concatenate thing and say, I can say equal to concatenate, okay, and I can say the standard proportion, quote, space, is, comma, this guy, okay, and I'm going to say standard deviations from the mean. And before I was going to have you say, hey, they're above or below, but I don't want to make this too complicated, and this makes my point. Okay, now the first thing you do when you say that, the most common mistake actually is if you don't have a space there, then these things all run together. So you actually kind of have to put spaces there. The next thing is like, okay, well, I don't need that to 16 decimal places, and let's see, I don't have a space there. So now we'll just go ahead and round that to, what should we round that to? 3 decimal places. So we'll say is equal to round, okay, and round says the number and then how many digits do I want to take it to, and we'll do comma 3. So I've got concatenate sample proportion is the value from the z-score and then standard deviations from the mean. Okay? We'll hit OK. We'll see this down here. And so now we want to say, okay, well, so we're just going to bring down the z. Okay, so now we want to say, what's the probability of a value being below that z-score? And the function that we're going to use here is we're going to use norm.sample.dist, this norm.s.dist, this guy, and cumulative. So we're going to choose true. So norm.s, and the s there stands for, we're using the standard normal distribution. Okay, and then if 83.91% are below that value of z, then I'm going to do 1 minus this is above that z. So 16% will be above it. Okay, so then I'm just going to say, I'm going to make this equal to that, but I'm going to do it also in percentages. That way it's sometimes easier to see. Okay, and then, okay. So no matter what I do, so now if I want to say, what's the value 0.3 or 0.6, I can get how many of the sample, what percentage of the samples will be below 0.6 and what will be above. Okay, and then we'll go ahead and sorry, so let's go ahead. I'm going to use the norm.dist here. So the this one, the norm.sdist, what it does is it standardizes that normal distribution to have a mean of 0 and a standard deviation of 1. This one, you can put in whatever you want, and so I'm going to go ahead and put in, we'll do norm.dist. And if you did all those ones where we had the height of the men and the height of the women, and are they in, can they fit in the cockpit or not, and so on. This one allows you to put in any of those values directly. So if we said if men are on average 5'9", so 69 inches, and with a standard deviation of 2.8, what percentage of men are going to be under 72 inches? Then I would say, okay, the x is the value I'm looking for, the 72 inches. The mean of the population mean I said was 69. That's 5'9". The population standard deviation at 2.8, and we're always going to want the cumulative distribution. And this says that 85% of men, 85.8% of men will be less than 6 feet tall, less than 72 inches. If the true population proportion is, or the true population is 69 inches with a standard deviation of 2.8. So now if we're going to use ours, I'm just going to do, we're going to use the sample proportion. Now I'm going to use the population proportion P, and I'm going to use standard error, okay? And I should get this exact same 95.53 right here, okay? So now it's all linked up. I can point it to, so if they say, well, how many are less than 0.55? So this way I'm doing it, I have to find the z-score first, and then what's the probability of finding a z-score this large? And then this one, it just says, look, you just tell me the population mean, the population standard deviation, our sampling standard deviation, which is this SE, and the sample mean, and we can go ahead and find it. Okay, so let's just go ahead and I'm gonna have you add a comment to yourself just to remind us of that. So we're gonna say insert comment. I can slide this around. We'll make this a little bit bigger, and we'll just say norm.s.dist assumes a standardized normal distribution, and it's standardized to mean equal to 0 and standard dev is equal to 1. Okay. Norm.dist allows you to use any population mean and standard deviation. Okay, so it's not normalized. You can use whatever you want. And it will give you the z-score underneath it. Okay, so then if I want to, if I always want to show that, I'm just going to hit show, and I can slide it around, and that way it would always just stay there. So why don't you go ahead and do that? That way I know you've done it. Okay, and if you don't like it there, you can later hit hide, and then it only shows up when you hover. Okay. Now, we want to do this sample size calculator and the margin of error. So what we're going to do right here is, and this presumed population proportion, we're going to end up using it both here and here. Okay, and what I say down here is this proportion that entered, the proportion you enter here isn't actually usually the value that you think you will actually find in the population. You have to put something in, and we're normally going to default to 0.5. And the reason is this goes back to what we saw on the previous page, which is assuming probability is 0.5, so they're split 50-50, provides the most conservative estimate, and so that's the one that is used in nearly any of these the survey sample size calculators that you use on the web. And I'm going to show you the Qualtrics and the survey system. You could also look at the SurveyMonkey one. But this is what we saw back here, that this gets maximized at 50-50, and so we need, I'll go ahead and hide myself, we need a larger sample size for any given margin of error at 50-50, and so that's what they assume. Okay. So this first one, what we're going to do is, for this first one, we're going to do the, this guy right here is the margin of error calculator, and then this one is the sample size. And I've given some confidence levels and z-scores right here. In fact, let's go ahead and we're going to name this range. We will go ahead and name this range confidence level. And these are the three, people use 90, 95, and 99%, and these are the accompanying z-scores. And so we're going to use this 0.5 here, and 0.5 squared is 0.25. So we're just going to do 0.25. So we're going to do, for each of these, 1.645 or 1.96, okay? And then what we will do is, but we'll start with this 1.96, and that way we can see if we match this 0.049 when we get to n of 400. So we're just going to say it's equal to, and I'm going to put the 1.96 last, just so I can make sure that I have everything in the order I want. So we're going to say this is equal to the square root of 0.25. Actually, let's make it more general so that we can change this population proportion in case we need questions answered with that. So I'm going to bring over my solution one right here and just show you. This one is going to this one is going to look a little more complicated, just because we're going to do p times 1 minus p divided by, in this case I've got n equal to 100, or whatever is in row 36, and then we'll multiply it by 1.96. And I'm going to go ahead and change this to, instead of being 0.5 times 0.5, I'm going to have it be 0.5 times 1 minus 0.5, just to make it general. So move that out of the way. So this guy is equal to, in fact, we'll go ahead and do this guy is equal to 1 minus that. How about that? Then it can do the math for us. So we're going to say it's equal to, let's do this times this divided by, for this first one, because I've got n equal 100, I'm going to put 100. And I'm going to put this whole thing in parentheses, and then I'm actually going to put square root. And I'm going to put that as an absolute and that as an absolute. Okay, and then we're going to multiply that whole thing times this guy, and I'm going to make that absolute, but I guess I just need to keep it in column D. And so then I've got that, and then all I need to do is, instead of making it 100, I'm going to make it that. And we'll leave this guy in row 36, so F4, and so we'll leave the $sign next to the 36. So now we'll do, okay, and that guy should be 0.049, 0.035, good. So now, is this correct? This, 800 times that. Okay, this is why it's actually better I prefer naming ranges, but it is, all right, Control Shift right arrow, Control C, Control V. Okay, so we've now got the confidence intervals for any of these, or sorry, this is the margin of error. So as I say over here, and I'll go ahead and move me out of the way, I calculated it for that one right there, this 0.049. And so I say if P is equal to 0.5, N is equal to 400, and we want the 95% confidence interval, so 1.96. Better change that. Okay, so now what I say is we're going to do 1.96 times 0.5 times 0.5 divided by 400, like the square root of that whole thing, and we should get 0.049 here, which means the margin of error is plus or minus 4.9 points. So if our survey, we found that 51% of respondents supported candidate A and 49% candidate B, the confidence interval for candidate A would be 51 minus 4.9 up to 51 plus 4.9. And if this were the case, you would say that candidates A and B are in a statistical dead heat or a statistical tie, or they're with the race is within the margin of error. They're neck and neck. Like, these are all things that if you're listening to the news, they should say, and they've gotten better about saying these things. You wouldn't want to say, oh, they're definitely in the lead, because you don't know, right? They're within that margin of error. And so especially if you're candidate A, don't rest on your laurels, because it's not clear that you're winning. If we were to go and take another sample of 400 different people, it could easily be 50-50 or flipped. Okay, so you just want to be careful about that. Okay, so now the reason I left this blank is I want to show you a cool feature, which is we're going to go up here to data validation, because I want to create a drop down. So we're going to use this data validation tool, and we're going to create a list. We're going to say you need to use a list, and I could type the values in for my list here, or I can say they're right there. Hit OK, and now you see this drop down, and so it'll pick 95% or 90. Like, I can just pick the values. I'm going to leave it at 95, and then what I'm going to do here is a VLOOKUP, and this is why I named that range. So I'm going to say, let's look up this value in our confidence intervals, confidence level, that's what we called it, and bring back column 2, and we're going to do false, because we want an exact match. Okay, so 1.96. Okay, and then, sorry, I meant for you to have to end up putting this in. And what we're going to end up doing is we're going to end up calling this the necessary sample size. This is the formula right here, and I'm going to split it out into a numerator and a denominator. And I'm going to go ahead and call this guy, let's call this guy, what do we have up here? We've got confidence, we've got sample. I'm going to call this one sample size Z, because I don't want to get this Z confused with this Z up here. So this Z is going to be the one that we're using to calculate our necessary sample size. And you can see that this is two different ways. These are actually saying the same thing. If you know that what P times N minus 1 minus P is measuring is it's giving us our measure of the standard deviation in the population. And so I wrote this out. These are both equivalent. And so in the numerator, we're going to say is equal to this times 1 minus that guy times sample size Z squared. And I'm going to put the sample size Z, I'm going to put that in parentheses. It shouldn't make a difference. Okay, the denominator is just going to be the square root of the margin of error, and the margin of error here, when we put it in, you enter into the formula here. I say it's like a 0.03 if you wanted plus or minus 3 points. So we're just going to take is equal to that guy squared. Okay, and so now when I divide this divided by that, it's going to give me a number. Like this says you need to do 84 people, and then what we're going to do is, haha, I just paused the recording because like that number is not right. What did I do wrong? And then I just realized up here I put in, instead of using sample size Z, I use sample proportion, which is going to give us a much tiny number, right? So we want to replace this with, let's go ahead and this guy is going to be sample size Z. That's my mistake. Okay. Okay, 1067. That makes much more sense. Okay, so the sample size, what we have to do is actually, the way they do this is if you have a fraction, you round that up. So that's 1067.1. Actually, we're going to end up rounding up to 1068 actually is the way they do it to be conservative. So we can either, so the way we're going to do that is Excel has a floor and a ceiling. So floor always rounds down, ceiling always rounds up. And so we just are going to do ceiling, and we'll do the ceiling.math because that's the more recent one. Actually, let's just do equals ceiling. And so what we're going to say is that number, okay? And then it's going to say, to what digit do you want us to take it to? And we just want it 1. So we just want it to put 1 just means to an integer. So now we say, okay, well, let's go ahead and check our work here. So I'm going to go ahead, let's go out to, you can click on the Qualtrics. This one, you can actually, if I just Google sample size calculator, these are the first 3 that come up. So let's go to the Qualtrics one, which I've already done right here. And so this says, let's just go ahead and we'll put this one right here, and we'll split these out. So we've got 95% confidence level, and I just wanted to recreate that drop down. Now this one, I think they default to something like 10,000 or 100,000, and if we do 0.3, it's going to give us ideal sample size of 1056, and if I keep doing out, it's going to do 1067, then 1068. So what I'll have you do is take a screenshot of this one or the next one, and the easiest way to do that in Excel is just to go up here and say insert, screenshot, and take a screen clipping. And then you just go boom. So again, and I'm going to go and put a picture border around that just to see it. But again, that's on insert, screenshot, screen clipping, and then it'll allow you to take a screenshot. So then to go ahead, let's go ahead and we'll see on our next, let's go ahead and we'll do, okay, we'll do this one. So if we want 95% and we want the confidence interval to be 0.03, now, if I leave the population blank, it's going to, oh, let's see, if I do 3, okay, if I leave it blank, and if I put, okay, now if I go to SurveyMonkey, so let's see, they have, this is my sample size at 95, and if I do 6, now this one, it's going to look like they have a number there at the beginning, but you actually have to type it in. Now, I'm going to just show you that how that number changes as I get my population size bigger. So if we now go make ours match 95% confidence level 0.06, okay, I get that same 267, and if I make the sample size or the population size, then the sample size keeps changing. Now, if I change this to, I'm going to take that, dial that back, and I'm going to put in 3, okay? And if I put 0.03 in ours, okay, it's going to say 1068, and that's as I make the sample size bigger, or the population size bigger, and that's because that finite population correction that we were talking about earlier, they're running that. And so if you actually look down to their formula, this is the formula they're doing, that z squared times p times 1 minus p, but they've got that big N there, they've got, this is that finite correction that they use down here in the denominator, and so they give you that. And so I just point that out. They have this nice thing to explain, and what is the margin of error and population size, and so they discuss it further, but I just want to show you ours will match theirs. And now we've got this great at least mine, I mean, this to me is fine, where, so now if I take a look at, let's go ahead and Now let's go ahead and look at how we could use this to do homework or answer questions and so on. So what I'm going to have you do is, if you go here to if we go down here to the week 3 what to know, and we see these practice problems on proportions and finite correction and the solutions, go ahead and download the solutions. I've already got them open, and I'm going to put this here, and then I'm going to put our calculator over here. Okay, I'm going to hide me for a second. Okay, but now on this question here, I can say this one says, look, you've got a population proportion of 0.45, and does it meet the normal distribution approximation for n equal 40 and n equal 80? So we'll do 0.45, okay, and at 10 it's not going to meet it, but at 40, okay, it will. And then if we look, and then at 80, so I say at 40 it's going to give you 18 and 22. At 80 it's going to give you, let's go ahead and look at what 80 is. Okay, and then if I go down here and do it for 40, you'll see that the standard error is 0.0787, which is of course what we get right there. Okay, and then if I scroll down, you say, okay, well, what is it when I put in 80? And you're like, boom, 0.0556. Okay, now the next one says, consider a population proportion of 0.85. So now, because this is more out in one of the tails, we're going to need to see probably bigger samples to make sure it works. So is it appropriate to use a normal distribution approximation for n equals 30? We say 30. Nope. How about 40? Okay, it works for 40. So that's what I say down here. And then with 40, we get 0.0565, which is what we get right there, right? Isn't this cool? I'm like, this is why we build calculator. This is why I built it, right? Because I'm like, oh, I would love to do, so, you give me any number you want. I'll just spit it back out to you all day long. Okay, so now it says, look, we took a random sample of 200 taken from a population with a population proportion of p equal to 0.48. So we can get the expected, and let's find this 0.0353. Okay, so let's do 0.48, and what is the sample size? 200. Okay, so yes, we get this 0.353. And then if we scroll down, we say, look, what the question is asking, if I took so now in this one what we're doing is say, okay, so the true population proportion is 0.48. How many if I do this 100 times, what percentage of those samples are going to come back with telling me the proportion is less than 0.45, even though in fact the true population proportion is 0.48. So this is just giving us a sense of how far off could we be, because we're actually never going to know what the true population proportion is. So we say, okay, but less than 0.45. So we say 0.45, and so this says, I calculate it. So the difference from 0.45 to 0.48 is a negative 0.03, which is what we get right there. The standard error is that 0.0353 that we get right there, right here, and we get that. Okay, and the z-score is negative 0.849 or negative 0.85, and so what we say is that this is 0.85 standard deviations below the mean, and so if I put that 0.85 in our normal distribution, we're going to get 19.79% or 0.1979, which we do. Okay, and you can run it. We run it the same way up here using that norm.dist. And then same thing if we say, what is it, how many will be greater than 0.55? Okay, and so here we get 0.07, same standard error, and so we get 1.981 standard deviations or z-score, and so that's 97.62%. And then when the question asks you something, what's between this 0.45, which is that red line here on the left, and 0.55, which is this red line on the right, we're going to find each of those and then take the 0.55 and subtract this one so that we're just left with the piece in between, and so that's 77.83%. Okay, we could do our finite correction factor question down here, which is with our finite correction, and it says, oh, I ended up deleting this. Let's go ahead and bring over mine. Okay, So if I say, what is it? The n is 500, okay, and sample size, a random sample of n is 70. Okay, so that's 14%. So yes, we do need to make the finite correction. Okay, and then depending on, let's see, our finite correction factor for that is going to be 0.2983. And so if we do, we're going to take this square root of 324 over the square root of 70, and if I multiply that out, so if I say that's equal to, I'm just going to do square root, and we're going to do is equal to 324 divided by 70. Okay, and then if I say is equal to this times our finite correction factor, okay, 1.9971, which is what we get over here. Okay, so hopefully, I mean, this has been a long video. I'm sorry that this is so long, but you're going to go out. I've got 5 questions out there in Canvas. You're going to go upload that. Make sure you've uploaded one of the screenshots of Qualtrics or SurveyMonkey or any of the ones that I give right here. So that we can, oh, and then this I just show here that if we do a sample size of, which one did I end up doing here? That at a sample size, so this first one was if the estimated P is 0.5, then I get that 1067, okay? And if I put it at 0.1, then it's 384. So I need a sample size 2.78 times bigger, about 2.8 times bigger. If the margin of error is around, or sorry, if it's about 50-50 in the population, and that's what I said. That's what I said right here, which is you're going to need a sample size 2.8 times bigger to get the same margin error if the population is split 50-50 than 90-10. Okay, and that's just because it's easier to say, come back with, is it the wrong side, 53-47, 49-51. If people are really polarized, it's 90-10. Then I can be confident with a much smaller sample size. Okay, so with that, this is long. I'm so sorry. We'll have you split this up, but wanted to show you that. Okay,